So what we're going to look at here is I'm just going to kind of talk through what the structure of a geometric proof looks like. It's no different than the other proofs that we've looked at, only this time our conclusions are the conclusions that triangles are congruent. And so you guys kind of looked at this, how these would be set just by finding the pieces and writing your congruent statements. Now we're going to put it into the form of a proof. So the first thing we're going to do is we look at the initial state that's provided. That will always be your givens, right? So no different from the proofs here. It's often useful to label the information that you have. So here I have that A, B, and C, D are congruent, so I'm going to write corresponding tick marks to represent that. I also know that A, D, and B, C are congruent. Right, the next statement that's created here is that BD is equal to itself, and we know that something's equal to itself by what? What's that property, if you can recall? Remember, it's looking at its own reflection, so it's a reflexive property. That is something is equal to itself. And by marking those three tick marks on that line, that shared line BD, what we see is that these two triangles are congruent to each other by which pattern? You have all three pairs of sides, so SSS is the pattern that we would use. So again, it's very straightforward. For something like this, you're looking for this process. And now, when we look at some of the other types of proofs, and I'm going to show you the one on the left, and then I'm going to have you do the one on the right, because these are proofs that are the same proof, or the same ultimate end state, but they're done slightly differently. Okay, and so I do want to show you several examples of each. So when we look at this, again, the first example that the first thing that we do is we check to see, is the first statement our initial state, the given information? It is, so we can write given for our reason, and we can label what we have. F, G, and GH are equal, so I'll mark those with the corresponding tick marks. And then it says, again, it's a word relationship. Okay? The word relationship is that GI, segment GI, bisects angle FGH. Okay? So there's nothing that you interpret in that given state. We're going to do that in the next step. So again, anytime you have words, definitions in your given state, I would interpret those as my next step. Even if they're not the next step on the proof, interpret it and find where that is. So the fact that GI bisects angle FGH means that what angles are the same? Here's GI, it bisects this angle. That means that these two angles are the same. So if I mark those as being equal and then I find, where does it show that FGI and HGI are equal to each other? It happens to be statement 2. It doesn't have to be. It could be statement 3. But here it is. And so I'm going to use the definition of the word that's written. And again, when you provide definitions, you have to use the word that appears in the proof. So the only word that appears right here is bisect. So that's going to be definition of bisect that justifies that statement. Okay, so right now I have two pair of sides, and I have one pair of sides and I have one pair of angles that are equal. So what I need to do is find one other pair of corresponding pieces. In this example to the left, it's GI is equal to itself. So that is, once again, reflexive property. Something is equal to itself. And now when I look at how this is set up, what I see is I have two sides, an angle, and this other side. The angle is between the two sides. So that gives me two sides with an angle between, giving me the pattern of SAS. Two sides and the A is between. And so that's the pattern I would use for this. So I want you to try the 4-step proof on the right. Again, it's just a really slight difference, but I want you to see if you can find what that is, or if you recall the wording to state what that is. Obviously on your homework and your quiz or your tests, it's just matching the drop down. Okay, but see if you can come up with your own reason for those last two statements. Right, so if we look at this, the first two statements are identical, right? So we start with our given. I'm going to go ahead and erase what's on here because I'm going to redo it. All right, so another possible way that you can complete this proof is if you know that FG and GH are equal, so I'll label that, and you know that the same relationship, that segment GI bisects angle FGH, and that means that these two angles here are going to be equal by definition of that word, bisect. All right, so same first two steps. But here, instead of saying that GI is equal to itself, this proof states that angle F and angle H are equal to each other. Well, what kind of a triangle do we know FGH is? If we look at it not as two separate triangles, but one whole triangle. It's what? So careful, the angles may, so if you're looking at this angle, it will turn into a right triangle. But what do we know about this whole triangle here, based on these two markings? Perfect. Okay, so this is an isosceles triangle, and what do we know about the base angles of isosceles triangle? The angles opposite equal sides of a given triangle are equal. Okay, and so that is the relationship here. So it's either base angles of isosceles triangle are equal, okay, or you might see the relationship that, and I'm going to rewrite it in a different word or set of phrases. It may be stated as in a triangle, angles opposite equal sides are equal. Okay, so these mean the same thing. Okay? So the fact that it wasn't established as an isosceles triangle probably means this is more likely the way that it's written, but it could be either of those. Okay, so that gives you the equality of angles there. And so now when you look for each of these triangles, you have a pair of angles and the side is located between it. So two angles with the side between gives you the pattern ASA for this one. Okay, so you do need to look at how things are labeled, look at how those labeled corresponding pieces are arranged or oriented, and use the pattern based on that arrangement. Right. Let's look at this final example. And again, I want to talk through the one on the left, and I'll have you do the one on the right. Or actually, I'll talk through both of them because they're just slightly different words for or justifications for the same relationship. Right. So once again, when you begin your proof here, we start with our given information. There's nothing specifically, no specific relationships provided, or no specific equation relationships provided, but there is two word relationships. So one, it says Q is the midpoint of PR. Let's look at that first. The fact that Q is the midpoint of PR means that it cuts that segment PR into two equal pieces. So PQ and QR have to be equal to each other. So that's the first relationship, and that's based on this word. So by definition of midpoint, we know that PQ and QR are equal. And then we also see that QT and PR are perpendicular. And so this is going to go in one of two directions, and that's what these two versions of this same proof give you, the two directions that this can go. The fact that QT and PR are perpendicular means that they form right angles, but you can express right angles either in terms of a word or in terms of an equation. So the first example shows the equation form. Okay? If you know that PQ and QT are perpendicular, then you know that this angle right here, angle 1, is 90 degrees. Okay? And we know that by the definition of this symbol, which is perpendicular. Okay? So by definition of perpendicular, we know that angle 1 is equal to 90. We also know that also holds true for angle 2. Okay? And now we've interpreted both of the word and symbol relationships that were in the given, and we can work with what remains. So next we have angle 1 is equal to angle 2. Remember, anytime you're looking for these, look to see, do they exist earlier in your proof? Angle 1 exists right here, angle 2 exists right here. Check to see, are they set equal to the exact same thing? Equals to 90, equals 90. If they are set equal to the exact same thing like these ones are, then the justification for this isn't just substitution, it is transitive property or substitution. And I know it's been a while. We did this in chapter 3, I think. So it's been a little while with proofs, so double check those. So now we have that these two angles are equal to each other. So we have a pair of sides equal. We have a pair of angles equal. The next piece is QT is equal to itself. Once again, reflexive property. And that gives us our third piece of information. In these, we have two sides, and the angle is between those two sides. So if we have two sides with the angle in between, side, side, angle between gives us our pattern of SAS. All right, let's look at, again, this final example here is the same proof, just coming at it a slightly different way, and the different way is just really the difference between in statement 3. The other way that you might see the perpendicular interpreted. Right, we still have our given. We still use the definition of midpoint here, and that's going to tell us that PQ and QR are equal. But now instead of putting it into the numerical equation form, that the right angles are created as 90 degrees, you might see that it uses the phrase, the wording, that angle 1 and angle 2 are right angles. This is still the definition of perpendicular. It's just a slightly different interpretation on it, but you would still justify it the same way. But once you move from that statement to this next, there is no place where angle 1 or angle 2 is written as an equation, so you're not using that transitive property or substitution anymore. But the relationship is a postulate that is established in the Euclidean or planar geometry. And that postulate, which again is just an assumed truth, it's a relationship that's accepted as being true, and that is that all right angles are equal. And so this right here, this phrase right here, can also be used to justify statements. It is a postulate, and it's not abbreviated. You'll actually see that whole phrase written out. All right angles are equal can be used to justify that angle 1 and 2 are equal if you know that they are right angles. Okay, so you don't specifically have to convert them into an equation first and then use transitive property. You can go directly to that postulate relationship that all right angles are equal. And then everything else remains the same. Once you have that labeled, QT is equal to itself by reflexive property, and then you have the same pattern, two sides with the angle between, which gives you the justification SAS.